let us look at the currents in the delta winding, IAH double prime, IBH double prime, ICH double prime. Can I express these currents in the delta winding in terms of the currents IAH prime, IBH prime, ICH prime? So, why we try to do that is finally we will get expressions for the currents that are fed to the entire 12 pulse LCC on the AC side. Say what I am talking about are these currents. I want expressions for this. We will show that there are some harmonics that get eliminated in these currents which are actually present in these currents. So, there are these currents which are fed to the individual 6 pulse LCC, there are some harmonics that get eliminated in the currents that are fed to the entire 12 pulse LCC. So, that is something which we are going to establish. So, to find the currents which are fed to the 12 pulse LCC, I know what is the current that is flowing, for example, here. Okay, let me just erase this. What is the current that flows here? Can I write an expression for this current in terms of a current which is already in the figure? Yeah, okay, I am talking about the current here. IAH into by N1, say it is in terms of this current IAH. Okay. So, I can write this as, say please note we have made some assumptions. If you recall, I also said that transformers are ideal. Please note our transformers are ideal transformers, no leakage inductance also. Okay. So, the two currents are related, and let us assume that these two transformers are obtained from 3 single phase transformers. So, if you take this YY transformer, it is obtained from 3 single phase transformers. If you take this Y delta transformer, it is obtained from 3 single phase transformers. So, this current is N2 by N1 into IAH. So, similarly, I can get the currents that are flowing here as well as here. So, here I show the currents as entering the dot. So, you are familiar with the dot convention, I suppose. In the other winding, the currents are leaving the dot. Okay. So, I will not get into those details of dot convention here. I presume you are familiar with it. So, this is N2 by N1 IBH, and this is N2 by N1 ICH. Now, what is the current that is flowing in, suppose I take this winding, what is the current here? So, instead of N2 I have root 3 N2 on the other side. So, it is root 3 N2 by N1 into IAH double prime. Okay. So, similarly I can show, okay, this is N2. The current that is flowing in this winding is root 3 N2 by N1 IBH double prime, and the current through this winding is root 3 N2 by N1 ICH double prime. Now, if I take the currents that are entering the 12 pulse LCC, that is the current I with a subscript uppercase AH. So, if I take these 3 currents, it can be written as sum of 2 currents. One is suppose I take IAH, it is N2 by N1 IAH plus root 3 N2 by N1 IAH double prime. Okay. So, let me write expressions for these 3 currents which are entering the 12 pulse LCC. Please note the 12 pulse LCC has a AC side which has only 3 terminals. Okay, though there are 3 terminals for the 2 6 pulse LCC individually, the entire 12 pulse LCC has only 3 terminals on the AC side. So, let me write expressions for this IAH, IBH, ICH. So, if I take IAH by Kirchhoff's current law, it is equal to N2 by N1 IAH plus root 3 N2 by N1 IAH double prime. Similarly, IBH is equal to N2 by N1 IBH plus root 3 N2 by N1 IBH double prime, and ICH is N2 by N1 ICH plus root 3 N2 by N1 ICH double prime. Now, this is okay, but I have expressions for IAH, IBH, ICH. I do not have expressions for IAH double prime, IBH double prime, ICH double prime. See, if you just go back to the previous page, the last 6 equations give expressions for IAH, IBH, ICH, and also they give for this IAH prime, IBH prime, ICH prime. But for double primed currents, I do not have the expression. So, how to get the expressions for, see, only if I get this double primed current expressions, I can get the current expressions that are actually feeding the 12 pulse LCC. Okay. So, can I write this double prime currents IAH double prime, IBH double prime and ICH double prime in terms of IAH prime, IBH prime, ICH prime by Kirchhoff's current law? Okay. So, how to do that? So, you take one of the terminals of the delta connection and apply, suppose I take one of the terminals. If you look at the circuit, IAH double prime minus ICH double prime by Kirchhoff's current law is equal to what? IAH prime. So, I am referring to this circuit. Please note, I am referring to this circuit. So, IAH double prime minus ICH double prime is IAH prime. Similarly, IBH double prime minus IAH double prime is equal to what? Equal to what? IBH prime. And ICH double prime minus IBH double prime is equal to ICH prime. So, these 3 equations are obtained by applying Kirchhoff's current law to the 3 terminals of the delta connected winding. But from this, can I solve for IAH double prime, IBH double prime, ICH double prime? I have 3 equations, 3 unknowns. Can I solve? Yeah, there are only 2 equations. Why? Why there are only 2 equations? Yeah. How? So, if you take so subtract the, do you get that? Say one is a linear combination of the other. If you can get one of the equations by linear combinations of other equations, but how do you say that I can get, say, for example, third equation from first 2? Yeah, if you add, for example, if I take if you just add, fine. Left hand side is fine. What about right hand side?
A plus B plus C is 0.
How? See, go to the circuit. How is it 0? See, A plus B, you are saying that IAH prime, IBH prime and ICH prime is 0? How? How is it 0? I mean, you should know how it is 0. 0 may be okay, but how?
There is no return.
Huh? See, I know only Kirchhoff's current law applied to a node. These are not currents flowing out of the node or flowing into the node. Yeah, we have the equation. Look at the equations. So, I have the equations, right?
Yeah.
From equation, I can say that IH prime plus IBH prime plus ICH prime is equal to 0. Okay. So, that means I can't solve for IAH double prime and IBH double prime and ICH double prime in terms of IAH prime, IBH prime, ICH prime using these equations, because there are only 2 independent equations. There are no 3 independent equations. So, I need one more. What is that? You can try solving. You can try to solve for these double prime currents in terms of single prime. You will see that there is a problem. What will be the problem? I mean, when it's actually less number of equations and more number of unknowns. Okay, so you can't get a solution that we want. So I need one more equation which is independent of these three. That the sum of these primed currents is double prime currents is equal to 0 if you apply KCL to this node. Okay, so from this node I get that IAH double prime and IBH double prime and ICH double prime add to 0, right? So that's obvious. So what I can say is, say there is a common factor root 3 n2 by n1. So if I ignore that common factor, it is not 0. So I can cancel out the common factor as long as it's not 0. It's not 0. So IAH double prime plus IBH double prime plus ICH double prime is equal to 0 by applying the Kirchhoff's current law to the neutral of the Y winding of the Y delta transformer. By KCL applied to the neutral of the Y winding of the Y delta transformer. So now there are no, I mean it's not 4 equations. I have to take say any 3 equations. So any 2 among these 3. Say suppose I take the first 2 and then this one. So if I solve these 3 equations for IAH double prime, IBH double prime and ICH double prime, I get it get the expression in terms of the single prime quantities. So if you solve, what do you get? IAH prime minus IBH prime. That's all. By 2. By 3. Please check, it is 1 by 3 into IAH prime minus IBH prime. So it's just solving 3 linear equations. 3 linear equations, the 3 unknown quantities are the double primed currents. In terms of single prime currents, you have to solve. That's all. So that is IAH double prime. Okay. Then did you get IBH double prime? IAH prime plus 2 IBH prime by 3. Okay, fine. Then ICH double prime. See, once you know the 2 double prime quantities, so it is equal to 1 by 3. So it is say I should take the, okay, what I am trying to say is this is minus IAH double prime minus IBH double prime. Now there is one more thing here. If you come look at IBH double prime, can I say that this is equal to 1 by 3 IBH prime minus ICH prime? Now this is because IAH prime plus IBH prime plus ICH prime from the expressions for these currents is equal to 0. So IAH plus IBH, IAH prime plus IBH prime is minus ICH prime. So I can write this as 1 by 3 IBH prime minus ICH prime. So if I want ICH double prime, so take the negative of IAH prime and take the negative of IBH, I mean take the negative of IAH double prime, take the negative of IBH double prime, add them and use this equation again, IAH prime plus IBH prime plus ICH prime, or okay, I need not even use that, I will directly get this. It's equal to 1 by 3 ICH prime minus IAH prime, because IBH prime gets cancelled. Okay, so that is straightforward. Now what I need to do is substitute this expression for IAH prime in this equation. Substitute this expression for IBH prime in this equation. and substitute this expression for all these are double prime currents, IIH double prime, IVH double prime and ICH double prime expressions have to be substituted here. Okay. So, I will just I need a very long page. So, I will go to the next page in order to substitute this. So, if I take IAH, it is equal to N2 by N1 IAH plus root 3 N2 by N1 into IAH double prime. Now, instead of IAH double prime, I write 1 by 3 IAH prime minus IBH prime. 1 by 3 IAH prime minus IBH prime. So, now you see that I have the expression for this IAH, which is the current on the AC side of the 12 pulse LCC, in terms of these known currents IAH, IAH prime and IBH prime. Now, I have the expressions for these currents. See, we got the expressions for these currents. IAH is IH at an angle 0, IBH is IH at an angle minus 120H and so on. So, I substitute these expressions now. So, this is equal to N2 by N1. IAH is IH at an angle 0 plus N2 by N1 into root 3 by 3 is N2 by root 3 N1. IAH prime is IH at an angle minus 30 degree into H minus IBH prime, we have the expression, it is IH at an angle minus 150 degree into H. Now, I need to simplify this further. So, for the sake of simplifying, I can't just keep a general expression, I have to take special cases, otherwise we will not be able to simplify. See, only if I go to special cases. See, what are the special cases? The special cases are fundamental and harmonics. H is 1 for fundamental and H is equal to 6k plus or minus 1 for harmonics. So, let me split this into two special cases. So, the first special case is for H equal to 1. So, when H is equal to 1, what I get is N2 by N1. So, H is equal to 1 means IH becomes I1. I1 at an angle 0 plus N2 by root 3 N1. IH becomes again I1 minus 30 degree into H becomes minus 30 degrees minus again I1 minus 150 degrees. So, this is the expression if H is equal to 1. So, H can also take the values of the harmonic component orders. So, in that case H is equal to 6k plus minus 1. Now, I will replace this H by 6k plus minus 1 only in the phase angles, not in the subscripts for the current magnitude, okay, it is not necessary. So, I will still write IH as IH itself, but when it comes to the second term N2 by root 3 N1 IH, I substitute here H by 6k plus minus 1 minus IH minus 150 degrees into 6k plus minus 1. So, this is the expression applicable if H is equal to 6k plus or minus 1 and k is equal to 1, 2, 3 and so on up to infinity. Now, the intention of going to special cases is simplifying. Say, now we can simplify. Suppose H is equal to 1, can we simplify? What is I1 at an angle minus 30 minus I1 at an angle minus 150? Huh? Is it I1 at an angle 0? Phase angle is correct. Root 3 I1 at an angle 0. So, okay, let me write one more step. N2 by N1, I1 at an angle 0 plus N2 by root 3 N1 into root 3 I1 at an angle 0. if h is equal to 1. Is that okay? Now, we see that it easily gets simplified. That root 3 gets cancelled, so it is nothing but 2 times n2 by n1 I1 at an angle 0. Now, if I want to simplify the other things, okay, let us see how to simplify this. For harmonics, it is n2 by n1 IH at an angle 0 plus n2 by root 3 n1 into IH. So, is there any simplification for this? Minus 30 degree, okay, let us first multiply this 30 degree 6k. Any simplification for minus 30 degree into 6k? Minus 30 degree into 6k. Minus 180k. Minus 180k. Now, okay, let me first write one more step. Minus 180 degree into k. Minus 30 into plus minus 1 will give minus plus 1. Minus plus 1 into 30. Minus plus 30 degrees. Now, one should note what is this order plus minus. If you look at the expression for h here, the expression for h is 6k plus minus 1. So, that means when you take plus sign in the expression for h, you get plus sign here. If you take minus sign, you get minus sign here also. Similarly, when you take plus sign in the expression for h, you get minus sign here. That is the point. See, the order of plus and minus is important. See, it actually means what is the sign you get when you get plus sign in the, when you take a plus sign in the expression for h and minus sign in the expression for h. Okay. Minus IH, okay, minus 150 degree into 6k. So, what do you say? One 50 into 6 is of course 900. 900k. Any simplification possible? Suppose I take minus 150 degree into 6k. Okay. So, this is minus 900 degrees into k. So, can I write this as minus 720 degree into k minus 180 degree into k? So, what is this 720 into k? K is an integer. K is a positive integer. So, minus 720 is 2 times 360. So, that is 0. So, this is equal to minus 180 degree into k. So, it is minus 180 degree into k. So, minus 150 into plus minus 1 is minus plus 150 degrees. If h is equal to 6k plus minus 1. K is 1, 2, 3, so on. Now, this can be written as, so if you take the first case h equal to 1, so the root 3 in the second term gets cancelled in the numerator and denominator. So, it is 2 times n2 by n1 I1 at an angle 0 if h is equal to 1. Okay. So, I forgot to close the bracket here. Okay. Now, what is a simplification of the case for harmonics? Can I simplify it further? Can I simplify this further? Yes or no? How? How can I simplify this? Any clue? Yeah, one should note that whenever k is an even integer, this becomes 0. 180 degree into k is 0 whenever k is an even integer, and whenever k is odd, it is minus or plus 180. Minus 180 and plus 180 are one and the same. Okay. So, there are actually two further special cases. So, I split this special case into two further special cases, one case being k odd, other is k even. So, let us do that. So, it is n2 by n1 IH at an angle 0 plus n2 by root 3 n1 into IH. So, what I will do is I will first take the easier case one first. Okay. Now, at this stage it may be difficult to say which one is easy, odd value of k is easy or even value of k is easy. Huh? Why? Yeah, even is easy. Yeah, it goes away. Okay, let us take even first then. So, it is equal to just minus plus 30 degrees, then IH at an angle minus plus 150 degrees if H is equal to 6k plus minus 1 and k is 2461. Okay. Now, let us take the odd values of k. So, it is n2 by n1 IH at an angle 0 plus n2 by root 3 n1 IH at an angle what? Okay. So, 180 minus plus 30. So, can I simplify that? What is 180 minus 30? See, what I have here is this. See, I can take minus or plus 180, the one is the same. See, whenever k is odd, it is 180 with a minus or plus sign, minus plus 30. So, 180 minus 30 is 150. 180 plus 30 is 210. So, this 210 is nothing but minus 150. So, can I say that it is plus minus 150? Okay. Minus IH. Similarly, k is odd. So, 180 minus plus 150 is plus minus 30. Plus minus 30. So, I will erase this steps. So, this is applicable if H is equal to 6k plus minus 1, k is equal to 1, 3, 5, so on. Let us take all these cases. So, the first case is as it is 2 n2 by n1 I1 at an angle 0 if H is equal to 1. Then the second case n2 by n1 IH at an angle 0 plus n2 by root 3 n1. Now, there are two cases here. See, one is IH at an angle minus 30 minus IH at an angle minus 150. I have to do this. The other thing is, say, when I take the top sign in the first term, I have to take the top sign in the second term also. Because top sign is minus means it actually means I am taking the expression for H as 6k plus 1. The bottom sign corresponds to H equal to 6k minus 1. So, I also need IH at an angle 30 minus IH at an angle 150. So, what is the first IH at an angle minus 30 minus IH at an angle minus 150? Root 3 IH minus 30 minus 0, 0. Then what about this case? Root 3 IH 0. So, whether it is the top sign or the bottom sign, what I get is root 3 IH at an angle 0. Is that okay? In both cases, I get root 3 IH at an angle 0. Okay. So, this is applicable if H is equal to, okay, let me just put this in bracket, this is just a intermediate computation. 6k plus minus 1, k is equal to 2, 4, 6, so on. Now, let us go to the other case. K is an odd integer. N2 by N1 IH at an angle 0 plus N2 by root 3 N1. Now, again I have two cases, IH at an angle 150 degrees minus IH at an angle 30 degrees, and the other case is IH at an angle minus 150 degrees minus IH at an angle minus 30 degrees. So, what is the first one? We can say it directly. Okay. Yeah, fine. Okay. So what do we get finally? So, in both cases it is root 3, 180. Okay. So, root 3 IH at an angle 180. So, this is if H is equal to 6k plus minus 1. K is 1, 3, 5, so on. Okay. So, we have come to the last step, 2 times N2 by N1 into I1 at an angle 0 for fundamental. If H is equal to 1. Now, if H is equal to 6k plus minus 1 and k is an even integer, then what is the simplification? So, you see that root 3 in the second term in the numerator and denominator gets cancelled. So, it is 2 times N2 by N1 IH at an angle 0 if H is equal to 6k plus minus 1, k is equal to 2, 4, 6, so on, and the last case is 0 if H is equal to 6k plus minus 1, k is equal to 1, 3, 5, so on. So, if you look at this expression, this is the expression for what? IAH. Please note, we started with this expression for IAH, one of the AC side currents of the 12 pulse LCC. So, what is this 0 for odd values of k? That means some of the harmonics are getting, not some, infinite number of harmonics are getting eliminated. There are infinite harmonics, half of them are getting eliminated. Okay. So, of course, one can verify what happens to IBH and ICH also. So, I will not go through the exercise for IBH and ICH. I will ask you to derive this. It is not obvious. Please note, expressions are not obvious. Even IBH, you can't directly say what is the expression for IBH by looking at the expression for IAH. Okay. If it is obvious, then you should be able to guess. Though some of them you can guess, you can, I mean, okay. This one I guess, I mean, this one should be possible, right? What do you expect? So, it is 2 times N2 by N1, I1 for H equal to 1, it is minus 120 degrees if H is equal to 1. Now, for harmonic with even values of k, what should be the expression? Can you guess? It appears as if, say, these are all balanced. So, the magnitude is obvious, but the phase angle is not so. So, it is 2 N2 by N1 IH minus, okay. So, I will leave it to you to verify that this is minus plus 120. Okay. So, if H is equal to 6k plus minus 1 and k is equal to 246. So, this minus 120 comes when you take 6k plus 1 and plus 120 will come if you take H is equal to 6k minus 1. So, that is something which you have to verify, and of course, when k is odd you get 0, that is something it is easy to guess. So, if H is equal to 6k plus minus 1 and k is 1, 3, 5, so on, you get this. Okay. So, even ICH is not obvious, the phase angle whenever the harmonic component does not get cancelled. So, I will leave it to you to verify. Thus, this is 2 times N2 by N1 I1 at an angle plus 120 degrees if H is equal to 1, and 2 times N2 by N1 IH at an angle what? Any guess? Plus minus 120. Again, please derive this. If H is equal to 6K plus minus 1, K is equal to 2, 4, 6, so on, and it is 0 if H is equal to 6K plus minus 1, K is equal to 1, 3, 5, so on. So, I am asking you to derive these expressions for IBH and ICH. I only derived for IAH. Now, if you look at the AC side currents of the 12 pulse LCC, then what are the harmonic components that are present? 6K plus minus 1 and K equal to 246. So, I can say that it is equivalent to harmonic of order H equal to 12K plus minus 1 for all positive integer values of K. Okay. So, the harmonic components in the AC side currents of 12 pulse LCC or of order H. So, instead of saying 6K plus minus 1 K is equal to 246, I will straight away say that it is 12K plus minus 1 K is equal to 1, 2, 3, so on. Is that okay? Now, these are as far as the harmonic components on the AC side is concerned. So, you see an advantage. The advantage is half the number of harmonics are getting eliminated. So, what the harmonics 5th and 7th which were there in 6 pulse are no longer there. The harmonic components 17 and 19 are no longer there. Okay. So, half the number of harmonics are getting eliminated. So, the dominant harmonic now is not 5th, it is 11th. So, this as far as AC side is concerned. What about the DC side? See, DC side there is, let me take the simple case of constant current on the DC side, then there is no question of harmonics in the current. But what about voltage? Voltage has harmonics. Now, if you take the 6 pulse LCC, the voltage harmonics are of order what? The DC side voltage 6K. Okay. Now, what do you expect for 12 pulse LCC? 12K. So, it can be proved, of course, that can be proved. Now, there is no question of fundamental on the DC side. What we have on the DC side is not fundamental. What is there on the DC side? It is the average value. Okay. So, what do you expect for the average value of the DC side voltage on the of the 12 pulse LCC? So, since they are connected in series on the DC side, look at the circuit. The minus sign terminal of the first 6 pulse LCC is connected to the plus sign terminal of the other 6 pulse LCC. So, since the two voltages these two voltages are appearing in series, the DC side or the average value of the entire 12 pulse LCC is sum of the averages of the two 6 pulse LCCs. So, that is obvious, but what happens to harmonics is the question. Now, for harmonics on the DC side, we take a different expression for H. So, for AC side we took H equal to 1 for fundamental, 6K plus minus 1 for harmonics. Now, we will consider only harmonics. There is no fundamental, there is a DC or average component. So, when it is having one, we are considering only harmonics, H is equal to 6K for K is equal to 1, 2, 3. So, this is on the DC side. Now, even in the figure we have written this, used this notation VH and VH prime. Now, I said that we are using this notation for, what is this notation standing for, VH or VH prime? I think say on the DC side H is equal to 6k for harmonic components. So, H is defined only for harmonic components. So, I am only showing the harmonic components in the figure. When I say VH and VH prime, it is not the average value. H is standing for harmonics. Okay. So, we are trying to analyze what happens to the harmonics. So, VH and VH prime are actually the harmonic components. So, can I get an expression for VH and VH prime? Suppose I take VH as VH at an angle 0. H is any harmonic component, 6th harmonic, 12th harmonic, 18th harmonic, anything. Okay. So, for each I take say VH as the complex VH as VH at an angle 0. Then what is VH prime? What is the magnitude? It is having the same magnitude. What about phase angle? Minus 30H, because the voltages that are applied to the second 6 pulse LCC are lagging the voltages applied to the first 6 pulse LCC by 30 degrees. The gate pulses are also delayed by 30 degrees. So, due to that, this is minus 30 degree into H. Okay. So, here H is equal to 6k and k is 1, 2, 3, so on. Now, these are the voltages on the DC side of the 6 pulse LCC. There are 2 6 pulse LCCs. Now, if I take the total circuit, it is 12 pulse LCC. So, what is the DC side voltage on the 12 pulse LCC? See, if I take any harmonic component in the DC voltage of 12 pulse LCC, can I get that from the expressions for the voltages of 6 pulse LCC? Huh? 2 times. See, if you look at the circuit, I have written expression, I have used a notation VH for the DC side voltage of the first 6 pulse LCC. I have used a notation VH prime for the on the DC side of the second 6 pulse LCC. Now, I want an expression for any harmonic component on the DC side of 12 pulse LCC in terms of these two. They are connected in series. So, it is VH plus VH prime. So, if I take the sum of VH and VH prime, what do I get? So, VH is VH at an angle 0 and VH prime is VH at an angle minus 30 degree into H. Now, we know that H is equal to 6k. So, k is equal to 1, 2, 3, so on. So, this simplifies to VH at an angle 0 plus VH at an angle 30 into 6 is minus 180 degree into k. K is equal to 1, 2, 3. So, how to do further simplification? So, split it into 2 special cases, even and odd. So, it is, if I take this easier case, even case first, it is VH at an angle 0 plus VH. So, when k is an even integer, this is 0. So, when k is equal to 2, 4, 6, it is 0, and it is VH at an angle 0 plus VH at an angle 180 degrees or minus 180 degrees, then k is equal to 1, 3, 5, so on. So, finally, this simplifies to 2 VH at an angle 0. So, what I am writing here is the expression for VH plus VH prime. So, it is 2 VH at an angle 0 when k is 2, 4, 6, and whenever k is odd, the sum of these two voltages is 0. So, we see that whenever k is odd, the harmonic components are eliminated, and whenever k is even, the harmonic components are just added. Okay. So, we can say that half the number of harmonics are eliminated. So, the harmonics that are present on the DC side voltage of 12 pulse LCC. So, the harmonic components on the or in the DC side voltage, in the DC side voltage or of order H is equal to, so instead of saying H equal to 6K, K equal to 246, what I will say is H is equal to 12K, K is equal to 1, 2, 3, so on. So, earlier we had 6th harmonic, 12th harmonic, 18th harmonic, 24th harmonic for 6 pulse. For 12 pulse it is 12th harmonic, the first harmonic is 12th harmonic, then 24th harmonic, 36th harmonic, 48, so on. Okay. So, there is a harmonic elimination on the DC side also. So, we see that there is some advantage with 12 pulse.